In this video, I'll be discussing the fourth lab in Physics 2212 on Faraday's Law. Introduction. This lab evaluated the effect of Faraday's Law on the time it took a permanent dipole magnet to pass through a tube of aluminum foil. The experiment was then modeled in GlowScript to further evaluate Faraday's Law with the magnet's velocity over time and the currents induced in the tube. To begin, a tube of aluminum foil was positioned vertically and a magnet of known dipole moment was dropped through the tube, with the time the magnet took to pass through the tube recorded. Here, the magnet's descent is slowed considerably while passing through the tube when compared to a magnet dropped without the tube. This procedure was then repeated 10 times, with the results averaged to a pass-through time of about 0.601 seconds. This brings us to the computational model. The computational model assumes a fixed tube with Newton's third law applicable to the force from the tube onto the magnet, a dipole moment in the negative y-hat direction, and negligible air resistance. The dimensions and characteristics of the foil tube and the magnet were inputted into a code template along with formulas for both the magnetic field of the magnet onto the ring as well as the magnetic flux through the ring, which would be used to determine the magnetic force from the ring's induced current onto the magnet. With iteration of flux for each ring of the tube, the magnet's velocity was modeled with respect to time. The results of the computational model show the variation in the velocity of the magnet as it slowed to a near constant velocity between 0.2 and 0.6 seconds. The model's pass-through time is 0.618 seconds, which is rather close to the real-world average of 0.601 seconds, with the difference likely due to imperfections in the real-world procedure. This experiment had minimized room for error, though some potential still exists. For instance, the video replay minimized the potential for human error when measuring time, but was limited by the frame rate of the video. Moreover, there may have been some imperfections in the aluminum tube shape or inaccuracy with the magnetic dipole moment's measurement. Conceptual questions. Which color of ring corresponds to clockwise and counterclockwise current as viewed from above? The blue rings below the magnet represent a counterclockwise current, whereas the red rings represent a clockwise current. This is because as the magnet falls the dipole moment in the negative y-hat direction, the rings below experience an increase in flux in the negative y-hat direction, resulting in a counterclockwise current to generate a magnetic field to counter the change in flux. Likewise, the rings above the magnet experience a decrease in the magnetic flux in the negative y-hat direction, inducing a clockwise current to counter the change in magnetic flux. What happens to the dynamics of the system when you flip the magnet around? Although the end results of pass-through time and forces on the magnet would remain the same, flipping the dipole moment results in the opposite changes in magnetic flux as those stated previously, resulting in the induced currents above and below the magnet switching, and thus ring color switching too. How does the total time of the tube of the real-world system compare to the model, and how might the model be made more accurate? Since the real-world magnet was small enough to fit inside the tube, the imperfect alignment of the magnet and the tube in real life likely accounts for the discrepancy between the experimental result and the computational model. Thus, considering multiple magnet orientations in the model may yield more accurate results. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? The initial decrease in the velocity of the bar magnet represents a nonlinear change in the acceleration caused by gravitational force being opposed by magnetic force due to the velocity-dependent induced current. Next, the system then reaches a constant velocity once the gravitational and induced magnetic forces reach equal magnitudes in opposite directions and thus zero net force. Finally, the bar stops and the velocity goes to zero. What-if questions. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? In this scenario, the induced current in the tube would increase dramatically and thus result in a stronger magnetic force in the magnet, which would further slow its descent, increasing pass-through time. What if holes or slots were cut into the tube? Would this affect the ring currents in your model? Here, the holes and slots in the tube would hinder the ability of induced currents to travel in closed loops around the tube, thus resulting in fewer eddy currents and less magnetic force on the magnet to slow descent, decreasing the pass-through time. In conclusion, this lab provided a deeper understanding of Faraday's law, observations on behavior of Lenz's law for falling dipoles in conductive tubes, and further insight into computational models for magnetic fields, flux, and induced currents.